discussion concerns an article from the forensic casebook regarding an electrician who experienced a severe electrical shock. The article's argument is that inadequate ground was a primary cause of the incident and that the electrician's actions were reasonable considering the situation. However, several criticisms have been raised against this argument. Firstly, the electrician's decision to proceed with work after receiving an initial low-grade shock and detecting a potential difference raises concerns. It is argued that a responsible approach would have involved thoroughly investigating the source of the potential before continuing any work. The electrician initially received a low-grade shock after contacting the enclosure and a car stop. The electrician used a wiki and found a potential between the enclosure and the car stop post. This led the electrician to believe the electrician simply need not touch the car stop as that was where the problem was. To stop there and proceed with work was irresponsible. Secondly, the investigator's conclusion that it was reasonable for the electrician to touch a second car stop, even after finding a potential on the first, is questioned. This conclusion is seen as making an assumption, and a dangerous one at that. Thirdly, the claim that an inadequate ground contributed to the accident is challenged based on the understanding of the ground electrode system's purpose. The ground electrode system or ground rod is not intended to clear faults or protect against energized equipment. Its primary function is to provide a path for lightning and to stabilize voltage to earth. In essence, the ground electrode system is there to reference back to earth, but is designed to not be used as part of the power distribution. When there is a fault, the overcurrent protection device will take place, and that usually takes place when there is a low impedance fault from the phase to the equipment grounding conductor. The analysis goes further to suggest the article lacks sufficient evidence to support its claims and points out a potential conflict of interest on the part of the investigator, who was working on behalf of the electrician. Now, let's consider what the function of the grounding electrode system is and is not. One key function is to provide a reference to ground, particularly for sensitive electronic equipment. This helps minimize electrical noise and ensure stable operation. The grounding electrode system also plays a crucial role in limiting voltage surges caused by lightning strikes or other transient events. By providing a low impedance path to earth, the system helps to dissipate the energy from these surges, protecting equipment and personnel. It is essential to understand that the grounding electrode system is not designed to carry large fault currents. That is the responsibility of the equipment grounding conductor, which is connected directly to the service equipment and the enclosures of electrical equipment. The equipment grounding conductor provides a low impedance path for fault currents to flow back to the source, allowing overcurrent protection devices to trip and to energize the circuit. The equipment grounding conductor's size is determined by the size of the overcurrent protection device and the applicable tables in the National Electrical Code, NEC. The grounding electrode system is supplemental to the equipment grounding conductor and is not intended to be the primary path for fault currents. When a fault occurs, the equipment grounding conductor provides the necessary low impedance path to quickly trip the overcurrent protection device, minimizing the risk of electric shock and equipment damage. It is also important to differentiate between grounding and bonding. Grounding refers to connecting electrical equipment to the earth, while bonding refers to connecting different metallic parts of the electrical system together to create a low impedance path for fault currents. Bonding helps to ensure that all metallic parts are at the same potential, reducing the risk of electric shock. All the bonding jumpers and connections should be tight, use star washers, and be properly torqued. The NEC provides detailed requirements for grounding and bonding to ensure the safety and reliability of electrical systems. These requirements are based on years of experience and research and are designed to minimize the risk of electrical hazards. Some common misconceptions about grounding include the belief that it is a substitute for proper insulation or that it will prevent all electrical shocks. While grounding does provide a level of protection, it is essential to maintain proper insulation and follow safe work practices to minimize the risk of electrical hazards. Another misconception is that a single ground rod is sufficient for all grounding applications. In many cases, multiple ground rods or other grounding electrodes may be required to achieve an effective grounding system. The NEC specifies the requirements for grounding electrode systems based on the size and type of electrical system. To ensure the effectiveness of the grounding system, it is essential to perform regular testing and maintenance. This includes inspecting grounding connections for corrosion or damage, measuring the impedance of the grounding electrode system, and verifying the continuity of bonding connections. Any deficiencies should be corrected promptly to maintain the safety and reliability of the electrical system. The grounding electrode system should be installed per NEC 250.52. This section lists what can be used as a grounding electrode. Firstly, a metal underground water pipe. Secondly, a metal and ground support structure. Thirdly, a concrete encased electrode. Fourthly, a ground ring. Fifthly, rod and pipe electrodes. Sixthly, other listed electrodes. The grounding electrode conductor needs to be sized appropriately, and this is defined in NEC 250.66. If connected to a rod, pipe, or plate electrode that is described in 250.52.5, the grounding electrode conductor is not required to be larger than 6 AWG copper or 4 AWG aluminum. If connected to a concrete encased electrode, as described in 250.52.3, the grounding electrode conductor is not required to be larger than 4 AWG copper. If connected to a ground ring, as described in 250.52.4, the grounding electrode conductor is not required to be larger than 2 AWG copper. Ground rods need to be a minimum of 8 feet in length and driven at least 8 feet into the ground. If rock bottom is hit, they are allowed to be laid in a trench at a 45-degree angle or be laid in a trench horizontally. Ground rods are connected to the system via a grounding electrode conductor, which is sized based on the size of the service entrance conductors, as defined in NEC Table 250.66. The minimum size of the grounding electrode conductor for a 200 amp service is 6 AWG copper if connected to a ground rod. Ground resistance testing is performed to measure the effectiveness of the grounding system. The goal is to achieve a low resistance to ground, typically 25 ohms or less. The testing can be performed using a 3-point fall of potential test. A ground resistance tester sends a current through the grounding electrode and measures the voltage drop. The resistance is then calculated using Ohm's law. The ground resistance test should be performed under dry conditions as moisture can affect the readings. The connections to the grounding electrode should be clean and tight to ensure accurate readings. If the ground resistance is too high, additional ground rods may need to be installed to improve the grounding system. Bonding is the process of connecting all metal parts of an electrical system together to create an electrically conductive path. This includes metal conduits, enclosures, and equipment frames. Bonding helps to ensure that all metal parts are at the same electrical potential, reducing the risk of electric shock. Bonding is required by the NEC in 250.92 and 250.96. The bonding jumpers need to be sized appropriately based on the size of the circuit conductors as defined in NEC Table 250.102. The bonding jumpers should be made of copper or other corrosion-resistant material. The bonding connections should be clean and tight to ensure a low impedance path. The bonding connections should be protected from physical damage. Bonding is important for safety and helps to prevent electrical shock hazards. When there is a fault, the fault current will flow back to the source through the bonding conductors. This will cause the overcurrent protection device to trip, de-energizing the circuit and preventing electrical shock. If the bonding is not properly installed, the fault current may not be able to flow back to the source, which could result in a dangerous voltage on metal parts of the electrical system. This could cause an electrical shock if someone comes into contact with the energized metal parts. Equipment grounding conductors, EGs, are sized according to NEC 250.122. The size of the EGC is based on the overcurrent protective device protecting the circuit. For example, for a 20 amp overcurrent protective device, the EGC needs to be 12 AWG copper or 10 AWG aluminum. For a 60 amp overcurrent protective device, the EGC needs to be 10 AWG copper or 8 AWG aluminum. For a 100 amp overcurrent protective device, the EGC needs to be 8 AWG copper or 6 AWG aluminum. For a 200 amp overcurrent protective device, the EGC needs to be 6 AWG copper or 4 AWG aluminum. For a 400 amp overcurrent protective device, the EGC needs to be 3 AWG copper or 1 AWG aluminum. For a 600 amp overcurrent protective device, the EGC needs to be 1 AWG copper or 3/0 AWG aluminum. For a 800 amp overcurrent protective device, the EGC needs to be 2/0 AWG copper or 4/0 AWG aluminum. For a 1000 amp overcurrent protective device, the EGC needs to be 3/0 AWG copper or 250 kcmil aluminum. For a 1200 amp overcurrent protective device, the EGC needs to be 4/0 AWG copper or 300 kcmil aluminum. The EGC must be installed in the same raceway as the circuit conductors. The EGC must be connected to the metal enclosure of the equipment. The EGC must be connected to the grounding electrode system. Ground fault circuit interrupters, GFCIs, are devices that protect people from electrical shock. They work by monitoring the current flowing in the circuit. If there is a difference of 5 mA or more between the current flowing in the hot conductor and the neutral conductor, the GFCI will trip, de-energizing the circuit. GFCIs are required in wet locations such as bathrooms, kitchens, and outdoor areas. They are also required on construction sites. GFCIs can be installed in circuit breakers or receptacles. Arc fault circuit interrupters of size are devices that protect against fires caused by electrical arcs. They work by monitoring the current flowing in the circuit. If they detect an arc, the FSI will trip, de-energizing the circuit. FSIs are required in bedrooms and other areas where people sleep. They can be installed in circuit breakers. There are different types of FSIs. Branch feeder FSIs protect the entire branch circuit. Combination FSIs protect both branch circuits and individual appliances. Outlet branch circuit FSIs protect only the outlets and the branch circuit. Surge protective devices, SPDs, protects electrical equipment from voltage surges. Voltage surges can be caused by lightning strikes, power outages, and other events. SPD work by diverting the surge current to ground. SPD are available in different types. Type 1 SPD are installed at the service entrance. Type 2 SPD are installed at branch panels. Type 3 SPD are installed at individual outlets. SPD are rated by their surge current capacity. The higher the surge current capacity, the better the protection. SPD should be installed by a qualified electrician. Electrical safety is everyone's responsibility. Always follow safe work practices when working with electricity. Wear appropriate personal protective equipment, PPE, such as gloves and safety glasses. Use insulated tools. Never work on live electrical circuits. Always de-energize the circuit before working on it. Test the circuit to make sure it is de-energized. Lock out and tag out the circuit to prevent it from being accidentally energized. Report any electrical hazards to your supervisor. Attend electrical safety training. The NEC provides a comprehensive set of rules and regulations for electrical installations. It is important to follow the NEC to ensure the safety of people and property. The NEC is updated every 3 years. It is important to stay up to date on the latest changes to the NEC. The NEC is available from the National Fire Protection Association, NFPA. The NEC is also available online. Electrical inspections are performed to ensure that electrical installations are in compliance with the NEC. Electrical inspections are typically performed by local government agencies. Electrical inspections can help to identify electrical hazards and prevent electrical fires. If you are planning to have electrical work done, it is important to hire a qualified electrician. A qualified electrician will be familiar with the NEC and will be able to perform the work safely and correctly. Ask the electrician for references. Check the electrician's license. Get a written estimate before the work begins. The electrical system is an important part of any building. It is important to maintain the electrical system properly to ensure the safety of people and property. Have the electrical system inspected regularly by a qualified electrician. Repair any electrical hazards promptly. Replace any damaged electrical equipment. Keep the electrical system clean and dry. A reverse polarity occurs when the hot and neutral wires are switched. This can create a shock hazard. If an appliance is plugged into a reverse polarity outlet, the metal case of the appliance can become energized. If someone touches the energized case, they could receive an electrical shock. Reverse polarity can be detected with a circuit tester. A circuit tester will have two lights. If the lights are both on, the outlet is wired correctly. If one light is on and the other is off, the outlet is wired with reverse polarity. If both lights are off, the outlet is not wired correctly. Reverse polarity should be corrected immediately by a qualified electrician. An open ground occurs when the ground wire is not connected to the grounding electrode system. This can create a shock hazard. If an appliance is plugged into an outlet with an open ground, the metal case of the appliance can become energized. If someone touches the energized case, they could receive an electrical shock. An open ground can be detected with a circuit tester. A circuit tester will have two lights. If the lights are both on, the outlet is wired correctly. If one light is on and the other is off, the outlet has an open ground. If both lights are off, the outlet is not wired correctly. An open ground should be corrected immediately by a qualified electrician. A short circuit occurs when the hot wire comes into contact with the neutral wire or the ground wire. This can cause a large current to flow, which can damage equipment and start a fire. Short circuits are typically caused by damaged insulation or loose connections. Short circuits can be detected by a circuit breaker tripping or a fuse blowing. If a circuit breaker trips or a fuse blows, it is important to investigate the cause of the short circuit before resetting the circuit breaker or replacing the fuse. Overloads occur when too much current is flowing through a circuit. This can cause the wires to overheat and potentially start a fire. Overloads are typically caused by plugging too many appliances into a single circuit. Overloads can be detected by a circuit breaker tripping or a fuse blowing. If a circuit breaker trips or a fuse blows, it is important to reduce the load on the circuit before resetting the circuit breaker or replacing the fuse. Aluminum wiring was used in many homes built in the 1960s and 1970s. Aluminum wiring is more likely to overheat than copper wiring. This can create a fire hazard. If you have aluminum wiring in your home, it is important to have it inspected by a qualified electrician. The electrician can inspect the wiring for signs of overheating and can recommend ways to reduce the risk of fire. Some common solutions include replacing the aluminum wiring with copper wiring, installing copper pigtails in the aluminum wiring, or using special connectors that are designed for use with aluminum wiring. Knob and tube wiring was used in many homes built in the early 1900s. Knob and tube wiring is not as safe as modern wiring. The insulation on knob and tube wiring can deteriorate over time, which can create a fire hazard. If you have knob and tube wiring in your home, it is important to have it inspected by a qualified electrician. The electrician can inspect the wiring for signs of damage and can recommend ways to reduce the risk of fire. Some common solutions include replacing the knob and tube wiring with modern wiring or removing the knob and tube wiring and installing a new electrical system. Electrical panels should be inspected regularly by a qualified electrician. The electrician can inspect the panel for signs of damage, such as rust, corrosion, or loose connections. The electrician can also test the circuit breakers to make sure they are working properly. Electrical panels should be kept clean and dry. The panel should be accessible and not blocked by furniture or other objects. Extension cords should be used only temporarily. They should not be used as a permanent wiring solution. Extension cords should be sized appropriately for the load they are carrying. Extension cords should be kept out of high traffic areas. They should not be run under rugs or carpets. Extension cords should be inspected regularly for signs of damage. Damaged extension cords should be replaced immediately. Light fixtures should be installed properly and securely. They should be sized appropriately for the room they are in. Light fixtures should be kept clean and free of dust. Light bulbs should be the correct wattage for the fixture. Overlamping can cause the fixture to overheat and create a fire hazard. Smoke detectors should be installed in every bedroom and on every level of the home. They should be tested monthly. Batteries should be replaced at least once a year. Smoke detectors should be replaced every 10 years. Carbon monoxide detectors should be installed on every level of the home. They should be tested monthly. Batteries should be replaced at least once a year. Carbon monoxide detectors should be replaced every 5 years.